Good day, viewers, and welcome to yet another interesting chemistry video. Because this is part 2 of the chemical combination. In case you missed the part 1, a link of part 1 will be provided in the description below, so you can check the link to watch the part 1. Of course, in this tutorial, I'll be taking you through coordinate covalent bonds, or we call them dative bonds, which is the third type of interatomic bond. Talking of coordinate covalent or dative bonds, these are bonds that are formed wherein both the electrons that are used in the bond are contributed by a single species. It's a single species that contributes both the electrons used. So from the word covalency, it also tells you the electrons are going to be shared. But in the sharing process here, it is only a single species that contributes both the electron. So the species that contributes is referred to as the donor species, and the species that accept is referred to as the recipient or the acceptor species. These bonds are characterized by indicating an arrow from the donor species to the acceptor species. So meaning the species that is going to contribute both the electron, which we refer to as the shared pair. So the shared pair or the bond pair is contributed by a single species. An arrow point from the donor, we have an arrow pointing from the donor to the acceptor. So the arrow points from the donor to the acceptor to indicate that this donor species is contributing both the electrons. Both electrons used. So both the electrons used are contributed by the donor atom. Before moving on to examples of some of these bonds, there are a few characters that we have to discuss, at least for the species that are participating in this type of bond. So the characteristics of species involved in a dative bond are: one of the species should have a lone pair or lone pairs of electrons. Presence of lone pair or pairs of electrons. That is one criteria for a species to partake in a coordinate or dative bond. The other characteristics is the other species, especially the acceptor atom, should have an empty orbital. So the acceptor atom should have an empty orbital. So let's look at some examples of this type of bond. So the first example we are going to look at is dissolving hydrogen chloride in water. So if we dissolve HCl in water, what happens? Dissolving HCl in water, HCl here, when dissolved in water, H2O, of course we know the hydrochloric acid, which is aqueous, and water is liquid. This guy here has, because it is a strong acid, it has the tendency of dissociating completely, meaning it undergoes complete ionization. So it breaks into the hydrogen ion and the chloride ion. Okay, so this hydrogen ion is what is going to react with the water to give us what we call H3O positive. This is a hydroxonium ion, or we call it a hydronium, or we call it an oxonium. ion. And then you have the chloride ion remaining. The bond that is formed between the hydrogen ion coming from HCl and water produces the hydroxonium ion, which is the H3O plus, and the Cl minus being the remaining species after the hydrogen have been detached from the HCl. Now let's look at the diagrams of how this one is formed, because we said one of the characteristics is the presence of lone pair or lone pairs, and then the acceptor atom should have an empty orbital. Now, water molecule, as we discussed in the part 1 of this video, it has a bent shape with oxygen bonded to 2 atoms of hydrogen, and then the oxygen having lone pairs of electrons. So what happened? The hydrogen ion coming with no electron at all. This is just an ordinary proton. So what happens? This proton is going to attack one of the lone pairs of this oxygen. It is going to attack this and then form a bond with it. So both these electrons that we have here are going to be shared between the oxygen and this hydrogen ion. So what happened in this case? You have oxygen, the central atom. This bond here, these two electrons that are present here rather, are going to be shared with this hydrogen ion. So when they are shared with this hydrogen ion, mind you, this hydrogen ion is coming now as an empty orbital. And this oxygen here has 2 lone pairs. So one of the lone pairs is going to be shared with this proton, which is just a proton that is inside and no electron at all. So this bond is going to be formed, and then you have one of the hydrogen atoms here, you have the other hydrogen atom, and then this one now, an arrow will be pointed towards this hydrogen. So because this species, this oxygen, is sharing 2 electrons with it, as these 2 electrons have been shared with it, this guy is going to become a +2 charge. It becomes a +2 charge. And then this hydrogen getting 2 extra electrons is going to be a -2 charge. But because the charges are equal, they will cancel out. And then only a plus charge remains here. So for that reason, you have this species with a positive charge, which gives us this particular substance, H3, meaning 3 atoms of hydrogen, and then you have the oxygen with a plus charge. So that is the reason the plus charge is found on the species. So this species is called a hydroxonium ion. Okay, you can call it a hydroxonium, you can call it the hydronium, or you can call it the oxonium. Any one of these names is acceptable in chemistry. So you either refer to it as the hydroxonium, or refer to it as the hydronium, or you refer to it as the oxonium ion. So this is an example. You see the arrow pointing. This arrow that is pointing demonstrates the dative bond that is formed, or the coordinate bond, because the arrow points from the species that is contributing both the electrons to the species it is sharing those electrons with. This is an example. The second example is dissolving hydrogen chloride in aqueous ammonia. So if you dissolve HCl in aqueous ammonia, this is the equation. Of course, when HCl reacts with NH3, this HCl, like we discussed in the previous example, will break into the hydrogen ion and the chloride ion. So this hydrogen ion component here, this H plus, and then you have the Cl minus here. So this H plus will then react with the aqueous ammonia, giving us the ammonium ion, NH4 plus. And then you have the chloride ion. This is also an example of a coordinate or a dative bond. but we are going to show an illustration of how this species, the substance is formed. Now you have aqueous ammonia, NH3. You look at its shape, it is shaped like this, with a lone pair here and 3 shared pairs with hydrogen. Is going to react with the proton coming from the HCl acid. So when this happens, these lone pairs of electrons here are going to be shared with this proton, the hydrogen ion, the H plus. And when these pairs of electrons are shared, because 2 electrons are going, the nitrogen gets a partial positive, which is +2, and then the hydrogen gets -2, but those charges are going to cancel out, and this charge stands. So you now have this shape is going to be altered because it was this lone pair that was responsible for this bent shape that we saw here. So when that lone pair is gone, you now have the hydrogen bonding with the nitrogen here, this other hydrogen bonding here, and this other hydrogen bonding here. Now this guy, nitrogen, is contributing both the electrons that are shared with this guy, which is a H. And this charge is represented here as a plus charge, okay? You can either put this in a bracket like this, and you place the charge up here, or you can just draw it and then you place the charge. So this arrow pointing from the nitrogen to the hydrogen indicates the coordinate or dative bond. This is the coordinate, or we call it the dative bond that is formed. And how questions are drawn from this in most cases is they'll ask you to show the formation of ammonium ion using illustrations. So you are expected to use this illustration. You begin from how ammonia is formed. You can look at the link in the description below to check the part 1 video. From there, you look at how it reacts with the proton coming from the acidic substance to give us the ammonium ion. This is an ammonium ion. And at times, what they will do, they will then ask you to state the type of bonds that are present here. Of course, there are 2 types of bonds here. This one indicates the coordinate bond, and these other bonds are normal covalent bonds. Okay, while this is a coordinate bond, a coordinate covalent, or we call it a dative bond. So this is how the ammonium ion is formed, by reacting ammonia and hydrogen chloride, which is hydrochloric acid. So let's look at the other example. The third example will be reacting ammonia and boron trifluoride. Now, boron trifluoride is BF3, ammonia is NH3. So these guys will form a bond here. The nitrogen becomes the donor species and the boron becomes the acceptor species. And how is this bond formed? Why in the first case, boron trifluoride is like this? Of course, from what we've seen in the previous examples, we know that the nitrogen has a lone pair of electrons. It has a lone pair, meaning the boron trifluoride should have an empty orbital. The ammonia molecule, we discussed it in the previous video, so you know how it is formed. And boron trifluoride here, boron is a species with 5 electrons. So if you look at the electronic configuration, so the first electron here, 1, 2, 3, 4, 5. You have 5 electrons that are coming here to form a bond. This is the ground state configuration. If this one is energized, this electron here in the 2s orbital is going to be promoted. One of them will be promoted to the 2py orbital. So it will move from this point here, and then it comes here. So you now have what? 3 spaces for bonds to be formed. So in these 3 spaces, in one of the spaces, you will have fluorine forming a bond here, fluorine forming a bond here, and the other fluorine forming a bond here. So what remains then? You have this empty orbital. You have an empty orbital there. So this empty orbital is what is now going to react with the lone pair of the nitrogen. So we represent it like this. This is the empty orbital in the boron. So these lone pairs of electrons are going to be shared with this empty orbital to produce an arrow points from nitrogen to boron, because it is nitrogen in the ammonia that is contributing both the electrons that are used in the bond. So the arrow points from nitrogen to boron. So this is the result that you get. So this is also an example of a dative bond, or we call it a coordinate covalent bond. These are some examples of coordinate covalent bonds formed. Of course, you should note that the bonds that are formed in coordinated compounds, these bonds can either be electrovalent, they can be covalent, and they can be dative. For example, of one that can be electrovalent, that can be covalent, or that can be dative is the ammonium chloride, which is NH4Cl. So one in NH4Cl, this bond, you have it to be covalent, you have it to be ionic, and you have it to be dative. Why do we say it has all of this? Now, the bond between ammonia and this hydrogen ion is a dative bond. And the bonds that are formed within the ammonia molecule, that is between nitrogen and hydrogen, are covalent. And then these ones will produce NH4+. So if these further react with Cl-, this charges becomes attracted, binded by a Coulombic force, giving rise to an ionic bond. So in NH4Cl, you have all these bonds existing in there. So you have in the formation of the ammonia molecule, 3 covalent bonds formed there. In the formation of the ammonium ion, you have a dative bond there, we call it the coordinate bond. And the ammonium reacting with the chloride ion brings about an ionic bond because of the plus and negative charge that are interacting. That's one. 2, the bonds can also either be covalent or dative without being ionic. They can just be covalent here, and they can be dative. An example is in the case of ammonium ion, or can be in the case of the hydroxonium ion. In the formation of ammonia, and this because here you have ammonia reacting with hydrogen ion. In the formation of ammonia, it is a covalent bond, and then in the formation of this ammonium, here you have a lone pair from this being shared with the hydrogen ion. In the hydroxonium, here you have water reacting with the proton, which is the hydrogen here. Here you have a covalent bond being formed between hydrogen and oxygen. They are covalently bonded. And the lone pairs, one of the lone pairs from these oxygen is going to be shared with the hydrogen, giving rise to the dative bond. So the bonds can either be covalent, ionic, or dative in coordinated compounds. Now, these two bonds, despite the fact that they are similar, covalent and dative, because both involves sharing of electron, there are differences as well. We can differentiate between them. And the differences between them in a covalent bond, both the species that are reacting are going to contribute electrons. So that brings about a mutual sharing. They contribute equal number of electrons. 1 electron apiece, or 2 electrons apiece, or 3 electrons apiece. Whereas in the dative, it is only a single species that contributes both the electrons used in the bond. And the other difference is that in the formation of pure covalent compounds, the species should have unpaired electrons. There must be unpaired electrons for covalent bonds to be formed. Whereas in the area of coordinates, one of the species should have a lone pair or lone pairs, and the other species should have an empty orbital. So these are the differences that exist between pure covalent bonds and a coordinate covalent, or we call it a dative bond. So from this, we'll move over to electron-rich species and electron-deficient species. Electron-rich species, we call them nucleophiles, and electron-deficient species, we call them electrophiles. The electrophiles are the electron-deficient species. The nucleophiles are the electron-rich species. Now, the electron deficient species, they are the ones that we are going to start with. We start with the electrophile. These are species, they can be molecules, they can be ions, okay, which has less than 8 electrons in its valency shell, meaning the number of electrons there don't take up to 8. They are not up to 8. The octet rule is not being met. So in species wherein you have the atoms or the ions not having up to 8 electrons in the valency shell, we refer to them as electron deficient species. Examples of electron deficient species: 1, we look at boron trifluoride, BF3. We look at beryllium hydride. We look at boron trichloride. These are examples of electrophiles, or we call them electron deficient species. These are species that needs more electrons. They want electrons, and we call them electrophile. Electrophile means electron loving. They are electrophilic in nature because they don't have up to 8 electrons in their valency shell, so they want more. So they are electron loving. And why did we say boron trifluoride is an electron deficient species? Of course, boron here has 5 electrons, configuration 2, 3. This 2 here is the core shell and the 3 is the valency shell. So boron forms here 3 unpaired electrons after it has been energized. So of these 3 unpaired electrons, you have fluorine coming around it. Fluorine coming with 7 electrons to form a bond. So the other fluorine also comes here. So basically, this is what you have here. Okay, you have this. A bond is formed between this guy and this guy. This is one bond. This is another bond. And this is another bond. Now you have an empty orbital up here. This is an empty orbital. It is this empty orbital that ammonia reacted with when we are discussing the formation of dative bond. So there is an empty orbital here. So if you check around the central atom here, boron has 2, 4, 6. It has only 6 electrons. So the electrons are not up to 8. So the octet rule is not being met. For that reason, boron trifluoride is an electron deficient species, or we call it an electrophile. So this is the first one. Second one, let's look at beryllium hydride, BeH2. In beryllium hydride, beryllium we know has 4 electrons. It is 4 electrons that beryllium is having, and with configuration of 2, 2. So in this case, beryllium here, Be the central atom, is going to be energized. So one of the electrons in the 2s orbital is going to be activated, and it moves into the 2px orbital. So it will then have 2 unpaired electrons. So the hydrogen will come here, form a bond with this, another hydrogen atom, bond here. So you have what? An empty orbital here and an empty orbital here. Okay, as in the case, if you look at it here, you have the first 1s, and then you have 2s, and moving over to 2p here. So you have 1, 2, 3, 4. When this is energized, this one moves from this point to this point. So the hydrogens will form a bond here, leaving these guys, the empty orbitals. Okay, so this is an empty orbital here, and this other one also up here is another empty orbital, as in the case of these 2 empty orbitals. So if you check around the central atom for beryllium, you have 4 electrons. It is only 4 electrons that are present. So that makes the beryllium hydride also to be an electron deficient, because it is having 2 empty orbitals here, which are devoid of electrons. So the valency electrons in the beryllium are not up to 8. So that means the octet rule is not being met. So the octet rule here is not being met at all. It is null and void. Next, the third one, we look at boron trichloride. BCl3 is also an example of an electron deficient species. Of course, boron, around the central atom here, you have just 3 electrons, which are unpaired electrons, and you have an empty orbital. So one of the chlorines will come and form a bond here. So this is what happens. This is an empty orbital. You have this to be an empty orbital here. This one, if you look around it, this is 2 electrons, 2 electrons, 2 electrons. So this gives us the bond pair or the shared pair, and you have an empty orbital here. So around the central atom, you have 6 electrons, also not fulfilling the octet rule. So for that reason, boron trifluoride, beryllium hydride, and boron trichloride are electrophilic, meaning they're electrophile. They are electron deficient. So next, let's look at the electron-rich species, the nucleophiles. Nucleophiles mean they want to move towards the nucleus. They are nucleus-loving, nucleophilic. They are nucleus-loving. They have excess number of electrons. They want to revert back to the nucleus. So the nucleophiles, we call them the electron-rich species. These are molecules or ion that has one of their atoms having more than 8 electrons around them. So it exceeds the octet rule. Examples of this species are we have phosphorus pentafluoride, we have sulfur hexafluoride, and then we have tetrahydrosulfate 6 acid. Now, phosphorus here reacting with 5 atoms of fluorine. Phosphorus we know is the 15th atom with configuration 2, 8, 5. The 2 and the 8 are core shells, and this is the valency shell. So phosphorus has 5 electrons around the central atom. So in this case, what happens? You are going to get the fluorine coming. One fluorine will form a bond here in your F. So this is how this guy is formed. Now, you look the central atom, phosphorus, the number of electrons are around it. This gives us 2, 4, 6, 8, 10. So you have 10 electrons in total surrounding the phosphorus atom. So we can represent it like this. We say P with a bond here to the fluorine, another bond here, another bond here, a bond down here, and a bond down here. So this is phosphorus pentafluoride, which is PF5. You have the central atom having more than 8 electrons. So this one goes above the octet rule. So that makes it a nucleophile because it is rich in electrons. The second one we look at sulfur hexafluoride, which is SF6. In SF6, sulfur is the 16th atom with configuration 2, 8, 6. These 2 and these 8 are core shells. The valency shell of sulfur gets 6 electrons. Represent the 6 electrons around it. And then you have 6 fluorine atoms coming to bond. Okay, this is what you have here. So you see this sulfur here forming a bond here, 2 electrons, forming a bond with this chlorine, this fluorine, 2 electrons here, 2 electrons, 2 electrons, 2 electrons, and 2 electrons. So if you look at the bonds, you have 1, 2, 3, 4, 5, 6 bonds. That gives you a total of 12 electrons. So there are 12 electrons around the central atom. So if you look at the diagram, it will look like this. You have sulfur as the central atom, sulfur here. You have fluorine, you have fluorine, you have fluorine here, fluorine, fluorine, and fluorine. So this is sulfur hexafluoride, okay? Because it is sulfur with 6. This is phosphorus, pentafluoride. This is sulfur hexafluoride, SF6. So these are all examples of electron-rich species. So refer to them as nucleophiles. And lastly, let's look at the tetrahydrosulfate 6. Now, the H2SO4, tetrahydrosulfate 6 here, sulfur is the central atom. Sulfur, being the central atom here, has 6 valency electrons. So we're going to represent the electrons like this. So what happens? In this situation, you have an oxygen atom here that's going to form a bond with the sulfur directly. You have another oxygen atom here forming a bond with the sulfur. And you have an oxygen atom here only contributing 1 electron. So you have this, because oxygen has 6 electrons around it. So each oxygen atom you are seeing has 6 electrons around. Another oxygen atom comes here. So in this situation, next, you have what? A hydrogen atom. So these ones here are going to form bonds, and these are how the bonds are going to be formed. Now, this here gives us a bond, this gives us a bond, this gives us a bond, this gives us a bond, okay? This a bond, this a bond, this a bond, this a bond. But we are only focused on the central atom, which is the sulfur. Now, if you look at sulfur here, the number of electrons, each bond represents 2 electrons. So let's look at the bonds in total. 1, 2, 3, 4, 5, 6. And 6 multiplied by 2, that gives us what? 12. So we have 12 electrons in all. So there are 12 electrons here. So this diagram can just be represented like this. Here we can say we have sulfur double bonded to oxygen here, single bond to this oxygen, and the oxygen single bond to the hydrogen. This oxygen also single bond and single bond here. So this is what you have. This is the H2SO4. Of course, you have H2S and 4 oxygen atoms. This is called tetraoxosulfate 6 acid. We call it sulfuric acid. So these are examples of nucleophiles, electron-rich species. So we now know that electrophiles, these are molecules or ions with their atom not having up to 8 electrons in its valency shell. And nucleophiles, we now know that these are molecules or ions with one of their atoms having more than 8 electrons around the central atom. So these are exceptions to the octet rule. We refer to this as an exception to the octet rule, meaning in these species that we've discussed, the octet rule does not hold. So there are exceptions to that, the nucleophiles and the electrophiles. So substances that are electrophilic and those that are nucleophilic are exception to the octet rule. So next up, we are going to look at comparing single bonds, double bonds, and triple bonds. We are going to compare these bonds under 3 different categories. One, we look at number of electrons. That's the first one. For number of electrons in a single bond, we know that each of the reacting species contributes an electron to a shared pair. So in a single bond, there are 2 electrons used, a maximum of 2 electrons in the formation of a single bond. In the double bond, each species there contributes 2 electrons to a shared pair. It is 2 electrons to a shared pair. So in total, you have 4 electrons being used. And finally, in the triple bond here, you have each species contributing 3 electrons to a shared pair. So total number of electrons used in a triple bond is 6. So you know that a single bond has less number of electrons compared to the double bonds and compared to the triple bond. So the triple bond has the most numbers of electrons The double bond has more and the single bond has less. So this is in terms of number of electrons. Now we want to look at in terms of bond length. How do we compare bond length in a single bond, in a double bond, and in a triple bond? Now, we just discussed that in a single bond, you have a maximum of 2 electrons that are being used. So in this case, you have the 2 nuclei of the species being pulled closer to each other by just 2 electrons. Because the more the number of electrons, the stronger the attraction of the 2 nuclei of the reacting species. So in a single bond, you have 2 electrons. In a double bond, you have 4 electrons. And in a triple bond, you have 6 electrons. So this tells us that you have more pull by the reacting species. The nuclei of the reacting species are going to be pulled closer to each other more in a double bond than in a single bond. Because in a double bond, 4 electrons are used. And I told you, the more the number of electrons, the stronger the attractions of the 2 nuclei of the reacting species. And in a triple bond, there are 6 electrons that are contributed, giving you 3 bonds. Of these 3 bonds, the 6 electrons used are going to attract the nuclei of the reacting species with a much more greater strength than in double bond. And in double bond with a much more greater strength than in single bond. So we can therefore say triple bonds here are more than double and double more than single. Okay, so this one here gives us increasing bond length. So meaning single bonds are longer than double bonds. This is single bond, double bonds, and triple bond. So this is longer, longest. So the single bonds are having the most bond length, double bond more bond length, and triple bond less bond length. So this is in terms of bond length. And the next one we look at in terms of bond energy. When we talk of bond energy, we are talking of the quantum or the amount of energy that is required to break that bond, to dissociate that bond. That's what we mean by bond energy. So that means the stronger the bonds, the more the energy that is required to break them, the less stronger, the less the energy required to break them. And we just discussed under bond length that in triple bond, there are 6 electrons used, meaning the nuclei are pulled closer to each other with a much more greater force than in double bond. So that means in triple bond, there is a greater force of attraction of the nucleus, which makes the bond stronger. And also, in a triple bond, we have 3 bonds there. Of these 3 bonds, the first one is a sigma bond, and the other 2 are pi's. They are pi bond. Okay, you have the sigma here, and you have the pi. So there are 2 pi bonds. So meaning these 3 type combining the sigma and the 2 pi's makes the bond much more stronger than in a double bond. In a double bond, you have just 2 bonds, one being a sigma and the other one being a pi. And finally, in a single bond, you have only one, and that is a sigma bond. Despite the fact that sigma bonds are stronger than pi bonds, but it is much more easier to break a single pencil than to break 3 pencils all put together. So that tells you to dissociate a triple bond, to break it down, you need more energy than the energy needed to break a double bond or the energy needed to break a single bond. So in terms of bond energy, which also means bond strength, this is increasing. The arrow here indicates the increasing bond energy. Okay, meaning to break triple bonds, you require more energy than the energy needed to break double bonds, and more energy needed to break double bonds than the energy needed to break a single bond. So this is how we can compare the single, double, and triple bonds in terms of number of electrons, in terms of bond length, and in terms of bond energy or bond strength. Next up, we are going to look at ionic character in covalent bonds.